Here's an explanation of why the inverse trigonometric functions have the domains and ranges that they do. Also, because I typed the word range, then I was offered this picture of mountains and it looks lovely. Arcsine and sine inverse mean the same thing. I'm going to be using both of them. We're going to rely on our trusty unit circle. Here's a unit circle, its radius is 1, quadrants 1, 2, 3, 4. Here's a unit circle, and here's a sine wave. And the point of the sine wave is that it maps out all of the y values from the unit circle, like this. They always stay together. They have the same y value all the way through. Now, it's the y value because it's the sine. When it's the cosine, we would be mapping out the x values. Here's the function y is equal to the sine of x, but we want to take its inverse. So if we want to take an inverse, we're going to reflect it over this purple dotted line where y is equal to x. And when we do that, we get this. Well, we have a problem with this. Taking a look at this. The problem with this is that this is not a function. It doesn't pass a vertical line test, which makes sense because my original function y is equal to sine of x is not 1 to 1. So what we're going to do is we're going to limit this to just this little piece. Now, this is the part of the sine of x that would be 1 to 1. So now when I reflect this over the purple dotted line, I get this. Now, this is the function that is the arcsine of x. This is what happens when I don't limit it to the 1 to 1 part. So this is not a function. This is x is equal to the sine of y, but this is the arcsine of x as a function. Note its domain and its range. The domain makes sense because the domain of the arcsine of x is going to be the same thing as the range of the sine of x, which would be from negative 1 to 1. But the logical reason behind why our range is from negative pi over 2 to pi over 2 goes back to the unit circle. So let's go back to the unit circle. So the inputs have to be unique. For every one input, I should get one output. So that means that I should have no repeat input values. So if I'm talking about the sine function, then I can't repeat any of my sine values. So let's look at quadrant 1. Quadrant 1, I have no repeat sine values there. Well, if I try to use quadrant 2, well, I've already reused those sine values. I can't use quadrant 2. Quadrant 3 is just silly. Let's look at quadrant 4. That has all of the rest of the sine values. Now, between quadrants 1 and 4, I have every single sine value that I could possibly need. So I'm not going to call this 3 pi over 2 to pi over 2. That would be silly because that's not continuous. Instead, we're going to call it negative pi over 2 to pi over 2, and it's nice and smooth. So that's why when I make my sine function 1 to 1 so that I can take its inverse, I'm going to use the values of negative pi over 2 to pi over 2 to limit it so that when I take the inverse, then I get a function. Moving on to cosine, I can't use the same quadrants. I can't use the values from negative pi over 2 to pi over 2. Because if we're talking about cosine, well, we've repeated our cosine values, so that's not useful to us when we're talking about cosine. So looking back at the unit circle, it would make sense to use quadrant 1, and where I don't have repeat cosine values, the next closest one would be quadrant 2. So foreshadowing for when we get to cosine, we're going to use the values from 0 to pi because that covers all of my unique cosine values. So the cosine just takes all of the horizontal components of my unit circle and plots the horizontal components out as a wave. So there's your cosine. We want to take this cosine wave and find its inverse. Now we're going to have the same problem that we had before, because when we want to find its inverse and flip it over this thing, well, it's not one-to-one. So when I do try to find its inverse, I get this. So that would be just, it's not a function, but that's what I would get initially. If I just took the whole cosine wave and flipped it over y equals x. So what I'm going to have to do, I'm going to go back to my cosine and I'm going to have to limit it. I'm going to say, okay, how much of this do I need for this to be one-to-one? Well, we already discussed what I needed in order to find unique cosine values all the way through. That would be this piece of it. So that is the piece that we are going to take, and that is the thing that we are going to find our inverse of. So when I flip this over y equals x, I should get this. And you can see visually that it is in fact the inverse of the piece of the cosine function that I'm taking, that is one-to-one. So there's my inverse, which is a piece of this, but this isn't a function, so we can't use all of this x equals cosine of y. We can only use this little piece. I remind you that, going back to the unit circle, if we want to find all of the cosine values with no repeats, we have to use quadrants 1 and 2. So that would be from 0 to pi. So the domain is from -1 to 1, and the range is from 0 to pi. When we want to make the tangent function one-to-one, then a couple things we're going to need to consider is that it's going to be defined everywhere that sine is one-to-one, because that's the numerator. Tangent is sine over cosine. So that means that we're going to look at quadrant 1 and quadrant 4, otherwise known as negative pi over 2 to pi over 2. But the other thing that's important is that we can't include the very ends of it, because that's where cosine is 0, and because tangent is sine over cosine. Well, whenever cosine is 0, then I'm going to have a vertical asymptote, and it's not going to be defined there. So right here at pi over 2, there's going to be an asymptote, and at negative pi over 2, I'm going to have an asymptote. This tangent function is clearly not one-to-one, so we're going to take a look at just the most useful piece right here. Let's toss in a couple of asymptotes there so we can see what's going on. So that is the limited piece of your tangent function with some asymptotes. So the inverse of this piece would be something reflected over this, y equals x, and when I reflect it over that, it looks like this. So that is the inverse tangent. Let's put some asymptotes in there. Note that they are now horizontal asymptotes. Now, because the original tangent function was not a wave with crests and troughs the same way that sine and cosine are waves, but instead it had an unlimited range, then the arctangent has an unlimited domain. And the range is very similar to the range of the sine of x, except that the sine of x included the endpoints negative pi over 2 to pi over 2. But the arctangent can't include negative pi over 2 and pi over 2 because there are asymptotes there. So non-inclusive. This is why the fictitious character Sheldon Cooper says he feels like an inverse tangent function approaching an asymptote, because it rises and then slows down as it approaches the asymptote and can't go any further, and also why the limit of the arctangent of x as x approaches infinity is pi over 2.